All right, here we are with example one. We are to calculate the volume of this pyramid. It is height 12 meters and whose base is a square with a side length of 4 meters. Okay, so we got a square base. And if we look down here, they already tell us that since this is a square, we can center this point. So treat this as the y-axis, let's say, the y-axis. And then this would mean that this distance here is 2, since the side length is 4. So for us, we want to somehow come up with an expression for the area of this square. So what I would encourage you to do is think of this, pretend that we have this sort of button for the value of y. So we've got this little button here, a little slider for y, where we can go ahead and move this button left and right. Sort of like on Desmos, when you have a parameter, you can just change the value of y. And imagine that we can go anywhere from y equals 0 all the way at the left end of the slider, and then we have 12 all the way at the right end of the slider. Or if you will, think of a dial. Okay, just think of a dial. And on here we've got 0, and then 1, 2, so on and so forth, all the way to 12. And imagine that and this is the y dial, and imagine that we can tune this or slide this back and forth, and that this square here will just go to whatever that y value is. So if we dial it down or move the slider to the left, then this square would move downward, and we would have something like this. Something like that. So our goal here is to not assume a particular value of y, but just work with y left to be arbitrary. So I'm going to just write this down and say we are going to, let's let y be a fixed but arbitrary value such that it is some number between 0 and 12. So some of you may be unfamiliar with this notation here, this little symbol. This just means within or possibly member of. And all we're trying to do is say that this is, assume that y is some fixed value, but it's arbitrary. So it could be 0, it could be 12, or any number in between 0 and 12. Okay? So with that, what we want to do is somehow figure out what the area of this cross-sectional square is ultimately as a function of y. So the first thing you want to do is just come up with an expression for the area. Sometimes it's easy to come up with an expression for the area, but it might be a little bit harder to see how you can rewrite it in terms of y. So initially, I'm just going to notice here that we have this side length here is labeled s. So I'm going to go ahead and just say that the area, A, is equal to s squared. It's the area, it's a square, cross-section is a square, so it's side length squared. But we need this in terms of y. So what we're going to actually do here is, might be a little hard to see, but in the diagram, there is this sort of triangle that's being outlined. So I'll do this one in red, but we have this triangle here. And that's what we are going to work with. Okay? Not only that, but there is a second triangle right here. So each of these triangles are right triangles, even if they don't look like it, but that's only due to the perspective of the diagram. So we really have two triangles. We've got this big red one, and then we have this smaller blue one that occupies the top half. Something like that. So essentially, these triangles are useful to us because they are similar triangles. Okay? So what we can do is, to make this a little bit more legible, I'm going to go ahead and draw these two triangles. One a little bit bigger than the other. I don't want to make it too big or too small because we still want this to be legible. So there's our expression for A, and now let's go ahead and label these things accordingly. So we know that this length on our red triangle is 2. So this is 2. And we know that the height of the red triangle, the big triangle, is 12. For the blue triangle, this smaller triangle right here, its height is this distance, and that's given to us. This is 12 minus y. So these distances are not always, or actually will rarely, if ever, be given to you. You have to come up with them on your own. This first example is more or less to get a big picture of the procedure, and then as we look at more problems, we will spend a little bit more time figuring these values out for ourselves. But I do at least want to mention how we arrive at this 12 minus y. Well, really, if we know this distance is 12, and we are at some y value, again, fixed but arbitrary, we're at some y value y, then this remaining distance is just the full distance minus the distance we have already traveled. Okay? So that's 12 minus y, and then this side length here, since it's a square, this interior length is just the side length divided by 2. So that is 1/2 s. All right. So what we can do is use similar triangles. So using similar triangles, we can say that the big height 12 divided by the little height 12 minus y, that is in proportion with the big base, let's say, so 2, divided by the small base. And I will write 1/2 s as just s over 2, because then we know that division by a fraction is multiplication by the reciprocal. So that boils down to 4 over s. So we have 12 over 12 minus y equals 4 over s. And of course, our goal here is to take this area that depends on s, and we want to make it a function of y. So we want to solve this equation for s, and then substitute that value in for s, which will then eliminate s from the equation. So to solve for s, I'll multiply by s, and then I will divide both sides by this fraction. So this would be 4 times the fraction 12 minus y over 12. And of course, this will reduce 12 minus y over 3. Okay. Now that we have that, we are free to import that into our area function. So what was a equals s squared, this will be changed into a function of y, which is going to be 12 minus y over 3 quantity squared. So then the volume, the volume of this figure would be the integral of the cross-sectional area with respect to y, and we would integrate over the full figure from 0 to 12. So I'm going to go ahead and just, I'll square this really quickly. Or actually, I guess we don't even need to square. I'll leave the top squared. I'll make that a 9 then. So then this will be 1/9, the integral from 0 to 12 of 12 minus y quantity squared dy. Well, we can do a u substitution here, actually, if we want to. So one way is to do the u sub, 12 minus y, to get du equals negative dy. So negative du is dy. The bottom bound of 0 becomes 12, and the top bound of 12 becomes 0. We're just plugging in these values, 0 and 12, into this expression for y to figure out what are the corresponding u values. Okay? At this point, we're going to go ahead and change the integral over. So this will be negative 1/9, the integral from 12 to 0 of u squared du. And then, of course, we can absorb the negative into the integral and flip the bounds to get 0 to 12. U squared du. Integrating, we have 1/9 times 1/3, so 1/27 u cubed between 0 and 12. So this is 12 cubed over 27. And the volume, so its units, would be meters cubed. And you can probably simplify this expression, 12/3 over 27, a little bit better. What do we have here? 12 cubed over 27. Well, 12 is 3 times 4 cubed. 27 is 3 cubed. So this becomes 3 cubed times 4 cubed over 3 cubed. 3 cubes cancel. So then this would be whatever 4 cubed is, which I believe is 64, I believe. Sounds right. So this would be 64 meters cubed. Okay.